Welcome to Oddly Real. I'm Nem Stefanovic. The presence of mass distorts the spacetime around it. We say that spacetime curves around mass. This curvature is what we experience as the force of gravity. But what exactly do we mean that spacetime is curved? Is it actually physically curved in some way? Interestingly, this is a real phenomenon that actually does change the geometry of spacetime itself. When we say that spacetime is curved, we mean that the geometry that we expect for flat space does not occur. For example, the angles of a triangle no longer add up to 180 degrees, or the ratio of the circumference to the radius of a circle is not 2 times pi. Somehow, space itself is distorted. However, it's not just space that is distorted, but time is distorted as well. A clock on Earth that is situated higher than another will run faster because it experiences a faster passage of time due to its position in Earth's gravitational field. Additionally, objects that travel through curved spacetime will naturally take curved paths rather than straight lines. Yet, these curved paths turn out to be the shortest paths through spacetime. In order to understand the curvature of space, we'll start by describing some simpler two-dimensional spaces. For example, imagine a two-dimensional being that exists only on a flat plane. This being only moves through the 2D plane and has no perception of a third dimension. It cannot leave the 2D plane, and it does not see outside of the plane. So the being is unaware of our presence as three-dimensional beings. Additionally, imagine that there are other kinds of spaces as well. For example, another two-dimensional being could live on the surface of a sphere. For the plane dweller, traveling the shortest path from one point to another is a straight line. For the sphere dweller, they also travel directly between 2 points in their space for the shortest possible path. From their perspective, they are going in a straight line. However, from our perspective in three-dimensional space, we see that the sphere dweller doesn't actually go in a straight line, but makes an arc between the points on the surface. Yet, this is indeed the shortest path between the 2 points. The sphere dweller knows this because if they deviate from that path in any way, the alternate path will be longer. Two-dimensional beings are also able to make and analyze geometry in their space. The beings discover that when a triangle is drawn, the angle should add up to 180 degrees. Additionally, when they draw a circle, the ratio of its circumference to its radius is always 2 times pi. Moreover, they also devise a simple process for drawing a square, which involves starting at a point, moving the length of the square, turning 90 degrees, and repeating this step until we arrive back at the starting point. Indeed, this checks out at any scale, small or large, for the flat plane dweller. However, the sphere dweller notices some anomalies when they try to draw these shapes on very large scales. For example, the being can construct a triangle that has all 3 angles equal to 90 degrees, and the sum of its angles equal to 270 degrees. Furthermore, circles have circumferences that are less than their expected values of 2 pi times their measured radius. Strangely, when the sphere dweller tries to draw a square by the process of walking around the edges and corners, one at a time, the end point and the starting point don't align. Their square does not end up being a closed object. We say that a space is curved if its geometries are different from the geometries of flat space. Notice that in the case of a spherical space, circles, triangles, and squares all differed from their expected geometries in a flat plane. Thus, the sphere is an example of a curved space. Interestingly, we don't need to have a higher dimensional view into a space to know if it's curved or not. In our example, the 2D beings don't see their world in 3 dimensions, yet they can still perform tests of geometry to determine if their space is curved. Let's define a measure for curved space and call it our curve. We can take the difference between a measured radius of a circle, our measure, and our expected radius of the circle in flat space, our expect. Let our curve equal our measure minus our expect, where our expect comes from the equation of a circle, or our expect is equal to the circumference c divided by 2 times pi. If the measured radius matches the expected radius, our curve is 0, so space is flat. However, if there's a difference, either positive or negative, then space is curved. In the case of a spherical space, our curve is positive. There are many possible geometries for space. For example, space could take the shape of a saddle. In this case, a circle drawn here would have a circumference that is greater than what would be expected given a measured radius. As such, it results in an R curve value that is negative. There's also an interesting example of a space in the shape of a cylinder. Since we can see the space in 3 dimensions, we see a physical curving around the cylinder. However, 2-dimensional beings that live within the surface of the cylinder do not see any curvature. In fact, they can draw all of their geometric shapes, including circles, squares, and triangles, such that their predicted values match the measured results. The curvature is 0 here, according to our definition of curvature of space, our curve. But how is that possible? Well, to see why, just imagine cutting the cylinder down its side and unrolling it onto a flat tabletop. Notice you get a flat surface exactly as the measurement showed. What about our real universe, where space is 3-dimensional? Can that be curved? Amazingly, the answer is yes. Where does it curve into? Well, interestingly, we don't actually need to know the specifics of this. Whether our space curves into a higher dimensional space, or if it just stretches or compresses within itself, or any other possible explanation, it's irrelevant for our purpose here. We can define the curvature of space as the difference between our measured geometries and the expected results for a flat geometry. Determining the curvature of space in 3 dimensions is more complicated than 2 dimensions. Drawing an object like a circle or a triangle can produce different curvatures depending on how the shape is oriented. However, we can use a geometric figure that's more natural for 3-dimensional settings, like a sphere. A sphere is defined by a constant distance from a specified point in every direction. The total area of a sphere is given by the formula area A equals 4 times pi times the square of its radius. We can rearrange this equation as the expected radius r expect equals the square root of the area A divided by 4 pi. Thus, we can define the curvature of 3-dimensional space as our curve equals the measured radius, our measure, minus the square root of the measured area of the sphere divided by 4 pi. This quantitative measure of the curvature of 3D space doesn't depend on any orientation, since a sphere is the same in every direction. However, it's a slight simplification since it gives us the average curvature in the space. If we wanted to know the specific curvature in every orientation in 3D space, we'd need to use more complicated math. However, this is quite sufficient for our purposes. Finally, we can link the curvature of space as defined above to the actual amount of curvature produced by matter. Here, we'll assume that there's a spherical region of matter where the matter is evenly distributed within. The curvature of space due to the presence of matter in the sphere is given by our curve equals the gravitational constant g divided by 3 times the constant speed of light c squared, and all multiplied by the mass in the sphere m. This equation for curvature due to mass is called Einstein's law for the mean curvature of space. What does this equation really mean? Well, notice that g and c are both just constants. So what it's saying is that space will curve proportionally by the amount of mass they're in. In fact, the constant g divided by 3c squared comes out to 2.5 times 10 to the power of minus 29 centimeters per gram approximately. That's the amount of curvature r curve for every gram of matter. So for example, if we take the mass of the Earth to be approximately 6 times 10 to the power of 27 grams, then the Earth has an extra 1.5 millimeters radius. That's pretty small. However, compare this to the curvature produced by our sun. In this case, our sun has an extra half of a kilometer of radius than would be expected if space was flat. What about above the Earth, away from its matter? The average curvature of space when there is no mass present is 0. However, that doesn't mean that there isn't curvature. Some orientations in the space close to the matter will still have a positive curvature in some directions and a negative curvature in others, even if the average is 0. The curvature of space, even away from mass, is what we feel as the force of gravity. So far, we've focused on the curvature of space, but we haven't discussed what happens to time. Recall that we don't just live in a three-dimensional space. In fact, we live in a four-dimensional space-time, where space and time are intermingled together. If space-time is distorted, we'd expect both space and time to experience the effects, and they do. To understand how time is influenced by space-time curvature, we first have to understand Einstein's principle of equivalence. This states that a uniform gravitational field is exactly equivalent to a system with a constant acceleration. So this means that if you were in a room without windows, experiencing a typical 1g force of gravity like on Earth, there'd be no way to tell if you were actually at rest on the Earth or if you were inside a rocket ship that is accelerating at a rate to produce 1g of force. Imagine you're on a rocket ship that is accelerating as it moves. The rocket ship has two identical clocks, one at the head called clock A and the other at the tail called clock B. Strangely, clock A will run faster than clock B. In order to see this, let's say clock A emits a flash of light every second. In the first flash, the light will travel towards clock B, but the rocket ship will also move forward, moving clock B in the direction of clock A. Ultimately, the light will have to traverse a distance L1. However, in the next flash of light, the same thing happens, except now the rocket is moving faster than before, since we said the rocket was accelerating. At this rate, the distance the light traverses, L2, is now less than the distance L1. If the time between the first flash and the second flash was emitted was 1 second apart from clock A, flashes would be separated by less than 1 second at the location of clock B. So clock A runs faster relative to clock B. Alternatively, if this experiment is reversed so that clock B emits flashes of light, then clock B would appear to run slower relative to clock A. Recall that Einstein's principle of equivalence says that this effect would also be exactly the same in a gravitational field. If you put two clocks on Earth, clock A high above clock B, then again, clock A runs faster than clock B. We can express this rate difference as the rate at the receiver is equal to the rate of emission times 1 plus Earth's gravitational constant of acceleration, g, times the height difference of the clocks, h, divided by the speed of light, c, squared. Finally, we can try to draw a rectangle in space-time as follows. We pick a height for an object and let it remain at rest there for 100 seconds. This makes the base of the rectangle from B to D. Additionally, let's take another object and place it up 100 meters higher than the first. Let it remain at rest there for 100 seconds according to clock A. However, Time moves more quickly higher up, so 100 seconds passes faster than at clock B. Thus, the world line is shorter since it takes less time to count to 100 seconds. Notice that if we try to complete the sides of the rectangle, they don't align. Our familiar notion of flat geometry fails. Spacetime is curved. In fact, you can see space-time curvature in action by throwing a ball a distance through the air. Notice the ball will trace out a parabolic path. This isn't surprising since we feel the force of gravity and we would expect it to pull against the ball. However, we now know that the force of gravity is the result of space-time curvature. In fact, the parabolic trajectory of the ball is the path that corresponds to the shortest distance through space-time for how the ball was set in motion. I hope you enjoyed this episode, and remember, oddly real, really interesting.